Okay, so we discussed Gibbons rotation today. Before I jump into Gibbons rotation, let us consider some figures. Just consider a 3-dimensional world to start with. When I draw these lines with arrow, those indicate axes. Okay. So, I have got these 3 orthogonal things, x, y, z. And now, suppose there is a vector, any other vector I put a dot on its top, so that you understand this is not an axis. Okay. Suppose its coordinate is x, y, z. I will write in a vector form column vector x, y, z, but here I am writing in horizontally x, y, z. Okay. So, if you take the perpendicular here, it is like this. So, we know this is x, this is y, and this that is z. Okay. This angle, I am putting an arrow, this angle suppose is theta in the direction shown. So, suppose the xy plane is moved in the opposite direction by minus theta, or equivalently this vector is rotated by theta. This z component remains as it is, this vector is rotated and the z component is dragged here. What will be the vector? That vector will then be the resulting vector, that is this fellow will be now translated, will be moved. This part will be rotated, this will come rotated here up to this fellow will come rotated, okay, and this guy will be dragged on that. So, you get this vector, that vector will lie in the x z plane then. If I do this kind of rotation of x y plane by minus theta, keeping z as it is, I will not touch z axis, and therefore, z coordinate of any vector will not get affected. Okay, I will not touch z axis, I will only keep z axis as it is, I will just rotate the x y plane. Can you see that? It is simple engineering thing. Hold the z axis as it is, rotate the x y plane by minus, where theta is shown like this. For the given diagram, this is the theta, so minus theta. So, that means this axis, I mean I told you yesterday, if you rotate a vector by some angle, it is equivalent to rotating the axis by the reverse of the angle. Sometimes it is easier to understand everything if you rotate the axis, if you see it by rotating axis rather than by rotating the vector, but both are equivalent. That is why I am trying to explain by rotating the plane rather than saying that rotating the vector. They actually will be rotating the vector, we will do rotation operation on the vector. Okay, but what is the effect? To understand that, I rotate the axis. So, that suppose I rotate the 2 axes, so x axis coincides with this, and therefore, y axis from here will be orthogonally pointing in this direction. So, this comes here x axis, and therefore, this fellow will lie in the x z plane. So, this fellow's coordinate, out of which some data will be there for x, z will be as it is, x will be changed, this much will be the x, but y fellow will be 0, is not it? So, I am saying rotate x y plane by minus theta. That means, I have a rotation operator now j theta Is that the correct? Take any vector x y z. Take any vector x y z. If I want to do rotate it, keeping the z axis intact, I will be actually rotating the x y this fellow by theta, and z will be, so resulting, what will be the resulting vector, rotate this guy. So, this fellow will be pointing here on this, and on that you add this vertical z component, whatever will comes, that is what I want to obtain. For you to understand, I explain it the other way, instead of rotating the vector, rotating the plane, because then it becomes easier to understand, but these two are equivalent. Okay. Actually, you are rotating the vector, but for you to understand easily, I see that if this rotated so that this axis coincides with this, orthogonal to that will be x, sorry, y. Okay. So, this will be the new x axis, and immediately this vector will be in the x z plane, new x z plane. That is the way it is understood very easily, but actually I will be doing the opposite. Actually, I will be holding the axis as it is, I will be rotating this vector, so that this comes in this line, vertical component remains as it is, add the two, that will be resulting vector. Okay. So, it is like, what will be the new component then? New component, if I draw, I have not yet operated the vector. Yeah, tell me quickly. Why are you bothered about sign? I am actually rotating the vector. I am rotating the vector. You remember what I did yesterday? I took one angle thing with angle alpha and then rotated from that by angle theta. Theta started from that line. This theta will be fine. This is actually class 10 or 11 question, you know, what you are asking. I have got one line with an angle alpha. If I rotate it by theta, yesterday didn't I do that? So, that theta starts from this line and goes like that. So, here also this vector theta starts at that, here it so happened because of my diagram it is in this quadrant, I have to rotate, align it to this. So, theta is pointing this way, but do not bother about the sign of the theta. I do not understand, this is a very simple question. I mean, I am very sorry that this question is back. So, what did I say? This is actually wasting time. What did I do yesterday? I said that this is angle alpha. This fellow, if I rotate, here I start and this is how I give the angle. Today I am saying that I am rotating in the opposite direction. But again, why are you bothered about what is drawn here actually? For this particular diagram, this is in this quadrant. It could have been in this quadrant, it could be somewhere else, isn't it? So, it is okay, cos theta, sin theta. So, what is the resulting thing? These things we started, I mean, I thought it is pretty simple. No? These things, this rotation and all we all study in schools actually, though I must say I have forgotten much of that. Okay, if I rotate it, so what is the after rotation, what is the thing, what results? I will be having a vector in this plane, isn't it? I will be having a vector in this plane. This new coordinate will be what? Y will be 0, z will be as it is, and what will be the x thing? That will be the length of this, only, isn't it? They call it p prime. So, p where p prime is square root of x square plus y square, simple geometry. So, that means this vector p prime 0 z, it is obtained by multiplying, by doing this, give it x y z, I apply on this operator j theta, I get this. This, you know, one value has been annihilated and 0 has come in, it is called annihilation. Y has been annihilated. Find the angle towards x in the xy plane. If you rotate by that, the other component will get, there is a y, you are rotating in the xy plane, find the angle towards x. If you rotate by the reverse of that, this x's or the vector by that, then in that plane the other fellow, y in this case, that guy will get annihilated. That is the thing, there is a rule. Okay. Is that fine? So, this is the length, this is that guy. Okay. Now, suppose this angle is alpha. Again, please see the arrow, whoever asking this question, please see again I am putting the arrow, because it so happen in this figure I will again rotate this vector. This is lying, this new vector is lying in the x z plane. I will rotate it now, so that this comes on x, and therefore, z value will be annihilated again. So, that is why I am taking the angle towards x, that angle is alpha, is equivalent to moving the x z plane in the opposite direction by minus alpha. So, that x axis coincides with this, and remember y is untouched, only y x z plane is annihilated, x z plane is rotated, all right. So, that means, I will now be rotating this, rotate whom x z plane by minus alpha, that is equivalent to doing actual rotation of that vector by alpha in the given alpha. Okay. So, I have another matrix here now j alpha. Acha, j theta is unitary, you all agree? Any rotation may make vector is unitary. It is unitary, na? 0 0 0 0 1, and this is the rotation part. Okay, you can easily see this unitary. J theta transpose j theta will be 1 man. Now, j alpha will be what? Y will be intact given any vector. Here it so happens this guy is lying in the x z plane, so is already annihilated, but for any other vector also I will not touch its y component. I am saying what I am going to do, I am going to just rotate only x z plane. So, given any arbitrary vector, not even the special vector where it is annihilated, given any arbitrary vector also, its y component will be untouched, only x z plane will be rotated. By what angle? By minus alpha, right, but y value will be intact. That means, this will be what? Cos alpha, because plane is rotated by minus alpha, the vector actually will be rotated by alpha in the opposite. So, cos alpha 0, very good, sin alpha, and 0 1, remember this is coming because y component has to be kept intact, and then this is minus sin alpha 0 cos alpha, again unitary. Okay. So, what this will result in, this thing, this is the thing, what this will result in is this. This vector, what is the component? That is j alpha times your p prime 0 z, don't be, I already started take the result from here, p prime 0 z, and what will that give rise to? The new x axis, new x, if you rotate it, so that this axis comes on this, then z value will be 0, because z is orthogonal, and new x value will be just the length of this. Let us call the length p. So, this will be p 0 0, where p is square root p prime square plus z square, which is same as the original length. Okay. So, vector, given a vector, two of its components will go by two successive unitary operations, in this case rotation of very specific kind. Of course, I have to find out theta and alpha, this need to be computed. Giving the vector, I have to find out the orientation and all those, and these angles need to be found out. That is a part of computation, mind you. This is coming graphically to you where I am giving the thing, but they need to be given a vector x, y, z, you have to find out those angles. That is not difficult. You know this is y, this is x, so you can find out tan inverse y by x, find out theta and all that. Okay. But this computation, it had actually, when you do adaptive filter also, this has to be done. That has some computational bottleneck, and then there are further versions of those adaptive filters where those computations also are eliminated or simplified and all that. There is research. I will not go up to that extent, you know. This initial, the very first category of Gibbons rotation based RLS adaptive filter will be dealt with, but there are further research I am telling you where those computations will be bypassed or simplified and all that. Okay. All right. So, obviously, you can now write p 0 0 is j alpha j theta x y z. These are matrices you can put here. Okay. J alpha, J theta is this product matrix also is unitary. Obviously, you take the overall transpose of that and pre-multiply, it will be unitary, isn't it? So, this is a unitary operator. So, that means norm square of this and norm square of this are same, and you can easily see norm square of this is p square, that is p square. Length has not changed, rotation after all those are fine. Now, instead of one such vector x, y, z, I will play a game, I will have two vectors now. Two vectors are given and I will be doing the rotation jointly on them, little complicated than this. Okay. Then we will consider the, from that we can easily consider the case of m number of vectors, not just one or two, m number of vectors. So, let us consider that case. Suppose, let me use this color. I wish I had some more color paints, this two color is too less. This is given. Now, two vectors, out of the two vectors, I am giving one, I am making life little simplified. One vector is given already in xz plane, no need to rotate it. I mean, xz is one vector is already given in xz plane, like this. This is one vector. Xz plane, so its coordinates are say x 0 z. It is already given. There already one y component is annihilated here. It is given to you. Xz plane, nothing in y, no nothing in that direction. It is lying in xz plane. But the other vector that will be given is not so simple. It is a general vector. It is like this, x prime, y prime, z prime. This is the situation. What I will be doing? I will be first concentrating on this guy. I will consider this angle theta. I will be rotating the x z plane without bothering about the other vector. Whatever happens to it, let it happen. I will only rotate this x z plane by minus theta, so that even this z is annihilated. Obviously, that will change the coordinates of this other vector also, isn't it? Nothing will be annihilated in general, but coordinate will be, of course, you have to write in the, but y prime will remain same. I am only rotating x z plane, y prime will remain same. So, I am saying rotate okay. That means again I write the matrix J theta. We have wrote in, whenever this cos theta comes, let us write C, and whatever sin theta comes S, every time cos and sin, but angles may differ, sometimes J theta, sometimes alpha, so that you substitute. You have it in your mind that C does not mean the same cos theta everywhere. So, just to I mean make the notation short, I am writing, the book also says C S minus S minus S and C. But here it will be with respect to angle theta, C means cos theta. If afterwards angle is alpha and again I read C, don't say it is, don't think it is the same C, okay, because it is the concept that is important here, not the exact values. That is why I will just shorten the notation. So, it will be C 0 S, okay. C means cos theta in this case. I hope you understand this. Borrow that theta from subscript of the resolution J theta. So, borrow the theta from here, apply that inside. So, C means cos theta, S sin theta, cos theta. Okay. Theta comes from here. So, obviously, what you get is So, you get that vector y prime that remains same somewhere. My figure may not be very good. Okay. I mean, do not try to find out the accuracy of my drawing, see the concept. Because if I really to make an accurate drawing, I need to spend some. So, I am just saying that this vector gets mapped to another vector, just another vector x double prime, y prime, z double prime. But I might draw it in a wrong place, that will not change anything, so do not find fault there. Okay. So, it will be in general somewhere. Say here, I am not sure whether it will be here or in some other place. Length also by mistake I am making much longer than this. Do not get into those things. Okay. This is that vector. What is important is what I write here, x double prime, y prime is important. I maintain the same y prime, z double prime. Okay. And this guy will be here, somewhere here. Actually, I am rotating this fellow by applying a rotation operator on this guy, and therefore, on this guy also. But effect will be easily understood if you view as though the plane is rotated, the vectors are held constant in their position. That is the easier way to understand. Okay. That is why I am always going that by that route. Plane is rotated by minus theta. Then you easily understand the orientation and all. But actually, x's are not changing. You are applying a rotation operator on each vector. Okay. So, that means, and this guy will be say p prime 0 0, p prime is simple square root of just length of this, and your is your j theta times okay. This is very weird. Now, please see, now what I do is very interesting. I have annihilated, you already gave me one value annihilated, I annihilated the other value also without caring for this guy. So, that it becomes something 0 0 and it is data. Now, what I will do, without disturbing this, I will annihilate z double prime here. How? I will now say that I do not want to touch this guy. So, keep x axis as it is, do not touch it, just rotate y z axis. How? Okay, you take the projection on this much is x double prime, you agree, vertical I have drawn, isn't it? This much is your x double prime, let it remain intact and find out this angle. This angle let be alpha. So, if I rotate the plane y z plane by minus alpha, then this axis will coincide with this, z will be orthogonal to that. So, that means in the new coordinate system this length only will be the y value, z will be 0, x will be as it is. Agreed? This is simply engineering operations, is rotation, nothing else. Can you see this what I am doing? I am now only moving the y z plane now. X z ho gaya, now y z. Z is common, z is my target. You will see, z is the last guy, is my target always. If I had x, y, something and z, then x z, y z, that something z, z is the last guy. Last, keep that in mind. Z is common. Okay, z is always to be annihilated. Okay, that is my x z I did. It was already annihilated here, and then here in this vector, I do not disturb x double prime, I do not disturb these x values. So, only y z plane is rotated. How? I find out what is the alpha. So, minus alpha direction, the plane is rotated, equivalently the vector is rotated by alpha in the given alpha direction. So, obviously, that will give rise to this figure. this is the thing, this vector will be somewhere here, this fellow, I mean do not please see the size and all, I mean I made it so big here unfortunately. This will come on, sorry, it will be the xy plane, sorry, this will be somewhere here, okay. This will be the xy plane, I agree. This projection actually, this I should have said this projection comes here. I just a slip of tongue. This projection, I mean instead of pointing at this, I pointed at this. This projection will be on this, because projection was in the yz plane. I rotated yz so that this y axis comes along with that projection thing. So, this is the projection thing, x value remains intact. So, it will be somewhere here, and our original guy is here. So, this will be what? Its x value will remain as it is, x double prime, y prime will be what? New y will be what? You can say p double prime and 0. What is p double prime? Length of this projection, norm square of this projection, because once y axis comes over this much becomes the y value, new y value, that is length, that length will be what? Euclidean norm, that square root of that Pythagoras you apply around, okay. All right. So, this is the situation. So, let us sum up that. So, what we did, suppose you have got two vectors put side by side, one was the given x 0 z, another is x prime y prime z prime, something like this is given to you. I apply first j theta on this and this is j alpha. Okay. What do I get? By applying j theta on this 0 gets annihilated and immediately I get x double prime. This is not x, this becomes p prime, no? This is p prime, norm of this, length of this, x square plus z square. This becomes some general value x double prime, y prime remain as it is, and this z double prime. And on that, so mind you, this data 2 zeros, but data, and then this fellow will be intact, this fellow will be intact. Here what will come? P prime 0 0 x double prime, here p double prime will come, where p double prime is square root of y prime square and this square, and this guy will become 0. So, what is the shape? Upper triangular, isn't it? And a chunk of zeros you can easily see. So, given this kind of thing, I will first rotate so that this is annihilated. Let the effect of rotation be something on this, I do not care, and then on this I will not touch the first guy, I will take these two, again rotate. So, first component will remain as it is, but rotation these two means what? A 0 will come. Okay. And this will be annihilated, fine, this guy. That is, when you rotate this vector by alpha, this is already 0, that will not give rise to anything, and this coordinate is untouched. Its effect will be on here where these are non-zero. Out of this will be annihilated, this will be replaced by the length of this part. So, I can now generalize this. Okay, now we have understood this. So, I will write the very general case now. Suppose you are given a situation like this, a general matrix is given like this, that a vector say x 1 1, then say x 2 1, x 2 2, x 3 1, x 3 2, x 3 3, zeros dot say x m 1 dot x m m, this is given to you zeros, and then zeros, then what is happening? I am suppose appending one row here, one extra row. say u11, say u1 not 1, u2, u3 dot 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 say um. Suppose this is a matrix, this is coming some way. How it comes, that we will see in the adaptive filter context. But we consider a very special case of this, where we had only 2 columns and immediately below this we had this u1 u2, u1 u2, x 0 y, x prime y prime z prime. That situation we took there, is it? I am more general. Suppose here first I consider these 2 fellows. This is in one plane for this axis and this axis, other values are 0. There I rotate it so that this is annihilated. So, some data comes, data is what? Square root of the square of this and square of this summed, and this guy gets 0. The effect of rotation on this fellow I do not care, let it be anything. Okay. This rotation, however, since I am rotating only this plane and this plane, that will not affect these values. Yeah, this is an extra thing that is coming. This will not affect these values. I am saying I do not care for the thing, but it is not that zeros will become non-zero, because I am only rotating this plane. So, this coordinate will change, this coordinate will change, but these values will not change, the 0 structure will not change. Then after doing that, so everywhere only first and last guys will change, intermediate guys will not change. So, this zeros they will remain as it is, but after doing the rotation I will be data and 0 here. On that, so suppose I do this some j1, j1 means you understand how to construct j1, some c 0 0 0 s 1 1 1 diagonal entry again minus s 0 0 0 c, you understand? I hope you do, I do not have to write it. You understand now what will be the structure? I mean cos theta, then all zeros from the sin theta, then a lower identity matrix, then again minus sin theta 0 0 0 cos theta. That I find out, that matrix I am calling J1. J1 will work on this guy, will give you a data and 0 here. Data is will be square root of this, but I am not bothered so much about what data comes. We know what it is, that is all. And first and last guys of other vectors will change, intermediate things will not change. That means, in short, I will have a structure after this. This is my rough site. I will have a structure like this. I will not write the exact values. I will have star. Star means non-zero. Please see, star means non-zero in my notation, and then zeros, zeros. And here will be star, star, 0 0 0, star. Then star, 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 0 0, star, dot dot dot, star, star, dot dot dot, star, zeros and star, right? This is my structure. Exact values I do not care. Now, target the second guy. Second guy I will be considering only these 2, and I will rotate, so that this guy is annihilated and this is kept fixed. I will only rotate this plane, the plane containing these 2 actually, they are corresponding to these 2 lines. If I rotate this and keep other other directions intact, those coordinates will not change. This value will not change, this value will not change, this value, other values will not change. In all the rows, only the second guy and last guy will change. Second guy is already 0 here, that will not get altered. Last guy, so the second and last. Okay, I will be rotating. So, I will annihilate this, and this will become square root of this and square of this. Okay. So, that will be J2. I am not writing J2, you understand, you can put cos theta sin theta in appropriate places. What will be 1 0 0 0 0, then 0 cos theta 0 0 0 0 0, niche one identity matrix, then 0 0, no 0 minus sin something like that, minus, second last, yes. Yeah, second and last. So, you can push that C and S appropriately. So, J2, J1. So, that means after that this will be as it is, then this 0 0 0 0 0, what will happen? This all zeros, this all zeros, and then I will target this guy. This guy, these three fellows, I'll these three axes I will consider. The corresponding plane will be rotated, so that this is annihilated. Other values will be intact. Okay. So, this way dot 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 j m if I do, you understood this? That will give rise to a structure like this, upper triangular structure. Then zeros, zeros, okay. This is upper triangular structure, this is the upper triangular part. So, just by m successive Gibbons rotations and given this kind of matrix, I can given this kind of, mind you, this is the given structure. How it comes, we will see. But given this kind of structure, I can make it just R and this chunk of zeros. Okay. So, keeping this in mind, now let us come back to that adaptive filtering. There will be zeros, because I did not tell you how many rows are here, how many zeros. Those rows plus one extra row, those will be, that will be given to you. But here it was not upper triangular plus one extra row and some rows of zeros. This will be converted into just upper triangular matrix and rows of only zeros. This is not a square matrix, but I did not give you a square matrix to start with. I will not be able to give you a square matrix. This will come from data. Yeah, tell me.
In case of the 3D world, we know what is the angle and but
here also it is very simple. When I take these two, I will find out, as though this is x axis, this is y axis, I will find out tan inverse y by x, cos theta sin theta, by that it will be unitary matrix. All those properties will follow in here also. Now, come to that optimal filtering case. What I said yesterday, that I had a very quickly, let me write down x, I gave x n, no? What is it, bracket n or subscript n, data matrix? X n was subscript n. This was the data vectors. I told you in the filtering case, these are not even defined data vectors, x n vector, z inverse x n, z inverse 2 x n, like that. Remember, isn't it? But here I am still trying to be more general, as though m defined columns are given. So, that becomes a special case of this. No problem, isn't it? X n, then I wanted to, this epsilon square n was d n desired response vector. This norm I converted into the conventional norm by writing out that delta part explicitly. Actually, you take d n minus x n into c n, that error vector, take the norm square. In that norm square, your lambdas would come. You remember, norm square of any vector in my definition will be what? That vector pre-multiplied by a lambda diagonal matrix 1 lambda lambda square dot 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 lambda to the power n. I gave it a name capital lambda subscript n, that times the given vector. So, given vector is the E n, lambda n, that is very quickly this norm square means, when I say use this norm square, this is the usual norm square, that is just square of the terms, each term and add, and this lambda n was this matrix, sorry, lambda to the power n. Isn't it? And remember one thing, can you see one fact? Can I write this matrix like this? I will be using this factor, this kind of division of the matrix. because I will be time updating from n minus 1th to nth, that is my goal. It was not lambda n actually, it was sorry, it was lambda n to the power half. This part is correct, let me correct this part. What we do there actually, E transpose n, this is my this is our actual norm square, isn't it? First term here, they multiply by lambda to the power n, and likewise. Then I say I factorize it as lambda n to the power half into lambda n to the power half by simply taking a diagonal matrix like this, lambda replaced by positive square root of lambda. If you multiply that with itself, the same guy with itself, you get this. And these are all symmetric matrices, we have diagonal matrices. Then the entire thing turned out to be equal to this, lambda n to the power half E n norm square. So, here lambda n I wrote like this very quickly, then lambda n to the power half, you can easily see can be written as lambda to the power half into isn't it? Instead of lambda, it becomes lambda to the power half, right? And this quantity we want to say, we know that this norm square is the usual norm square. So, that norm square will remain intact even if you pre-multiply by a unitary matrix. Okay, so, this will be same as some q n times the same thing. Q n has to be any q n is any unitary matrix, but we will choose it appropriately. You break it up, q n into this d n minus q n C subscript n or capital N, what did I choose? A C parenthesis n or parenthesis n? This is the norm square. This is what we minimize to get the optimal common coefficients, isn't it? Then I said that we should choose q n very quickly. What do you say? We should choose q n so that this matrix is converted into an upper triangular form by q r, at least q r factorization exists, we know. From that Gram-Schmidt orthogonalization point of view, I gave you that existence actually, that you can really have those orthogonal vectors and you get a q r form. Okay. And it is square. So, this will give rise to, this entire thing will give rise to what? One matrix like, this is yesterday's material, but I need to recall that to apply today's theory. R n and the zeros, R n was that upper triangular part, isn't it? This times C n, and q n times this vector I decompose into two part, upper part, lower part. Upper part, this is the m cross m. So, upper m into one part, I call it small u n upper, and lower part was l n. And this entire norm square, what is the minimum? When it is minimum, then only I will get the optimum. The entire norm square will be what? Lower part square, lower part norm square. This thing I wrote like this, u n dot 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 l n. Okay. So, what is the total norm square? That is l n minus 0 l n and u n minus r n c n, that is the upper part, and norm square of this lower part l n square, which is independent of c n plus upper part. So, that means you choose c n so that upper part norm square is minimum, u n minus r n c n. So, minimum possible is only when 0, norm square cannot be negative. 0 means if you can find out by solving equation r n c n equal to u n, then that is the optimal one, isn't it? So, that is how we find out, right. That is what I said yesterday, and the square of norm square of ln will give you the corresponding error with those projection error. Okay, that is where I stopped yesterday. Now, suppose by hook or crook you know appropriate q n at nth index, n minus 1th index. So, that is an n minus 1 cross n minus 1 matrix, but that you know. What was that matrix? That was that took delta n minus 1 to the power half x n minus 1, that matrix it converted into this kind of form, upper triangular R n minus 1 and 0. This is always m cross m, because number of columns in this is not changing, number of row may change, but number of column is m and upper part is m cross m, that is not changing. Number of coefficients is m. You have to solve this part. So, the size of the equation does not change, this length of the zeros change, I do not care. Okay. So, suppose by hook or crook I know that q n minus 1. If I know that, then what I do, I form first one matrix q zero zero. Actually, it should be 0 transpose, this is a row vector and this is 0 column vector, and you call it q bar, you could book it n minus 1 or n, so the q bar n minus 1. If I take this first, if I take that matrix, if I apply, take that matrix and apply that on this part, instead of q n, I have to come at the appropriate q n. I am coming step by step. First take that matrix, apply on this guy. What results? Let us find out. That is q n minus 1 into delta this lambda a to the power half x n. What is appropriate q n is our goal. What is appropriate q n? Given q n minus 1. What should be that q n? Okay. But I am just doing some experiment. I am saying suppose I construct a matrix like this and see its effect. What will I get? Look at the structure. Q bar n minus 1 into lambda, this factorization we have already seen, and this q bar n minus 1, and your x n matrix is what? X n minus 1 and some data, nth index value of x 1 n, nth index value of x 2 n, this I am writing separately, no problem. This x n, what is the x n matrix after all? Upper part I write x n minus 1, data collected up to n minus 1th index, and then this is x 1 n, x 2 n, dot dot dot. Instead of writing all that, I am putting star. Okay. Now, consider this you should be able to understand. This part times x n minus 1 and 0 will multiply this, that will be the upper half, and then zeros will multiply this 1, that is how this product is formed. Forget about the lower part first, consider the upper part. This chunk times this and 0 into this will not give rise to anything. So, this into this, that will be upper part, and that will be again multiplied by this, 0 will multiply the lower half. So, can you see this, or do we have to work out the steps? Do you have to work out these steps, or I do not know. For some of them I know you are very fast, but for others I am not, at least silence does not convey much, you know. So, this would be lambda to the power half, sorry, it was lambda, you correct me. As a matter of fact, I am teaching this for the first time, you know, I do know this, I never taught this in the past. Then VLSI it was quadic, not this. And this star star star, right, isn't it? Now it understood. Now you substitute this, those zeros will multiply the last column, forget it, q n minus 1 times this, what will that give rise to? What is q n minus 1? The one which worked on this guy, this lambda to the power half you take out, is a constant. So, q n minus 1 worked on this, q n minus 1 worked on this, but what is q n minus 1? It is the one which was correct, which worked on this matrix, make it an upper triangular 1 and some zeros. Okay. Upper triangular part was m cross m in size, that is never unchanged, that is never changed. Okay. So, that will give rise to what? Lambda to the power half r n minus 1, then there will be zeros, but zeros total number of 0 1 less than here, and then the stars, this row times these columns if you have, the stars will come up, those last datas. All right. So, what kind of form? Upper triangular lambda to the power half you forget, or you absorb in this, So, what kind of form? Upper triangular followed by a chunk of zeros, and this is your x latest data x 1 n, this is your x 2 n dot dot dot, this is your x m n. So, if I construct this matrix, apply on this, I get this. Okay. Now, I apply Gibbons notation. I take first row, annihilate this guy, sorry, first column, annihilate this guy, one rotation. Then take the other row, next row, second row, I mean, say next column, second column, and second row fellow and this last fellow. I consider that plane and annihilate the last guy, so on and so forth. So, I apply the sequence of rotations, Gibbons rotations, m number of rotations, I get back a perfectly upper triangular matrix and then followed by chunk of zeros. So, that means, if I now take this and have j m, now I put n by the way, because all that data depending on data up to index n, j m n j 2 n, j 1 n into this q bar n minus 1. This part let us call it T n. So, T n into q, this is my q n. Okay. So, coming to this equation, this is our equation. I know what is q n now. It is, this is equal to T n, this is that product of those rotations which is an unitary part. T n is unitary, and remember, yeah, one thing I forgot to mention. This matrix also unitary. This was unitary, just as 0 and 1 does not change anything. This still remains unitary. I absorbed it in an identity kind of matrix, isn't it? So, this product is unitary, after this rotation only. So, this is T n into your q bar n minus 1. We know the structure of q bar n minus 1, q n minus 1, zeros, zeros, 1. So, that means the same applies to this q n also, isn't it? This lambda n to the power half d n, this again in the by the same logic we can write as, by the same absolute same logic, we can write as lambda to the power half okay. And then on this if we apply this T n, just 1 or 2 minutes on this, then what do you get? This part is this into this, 0 into this does not matter, and then 0 into this and 1 into this. So, the resulting is a vector where this into this comes on top, that will be multiplied by first q n minus 1 okay. That component we already obtained earlier, that component we already obtained earlier, that is if you know q n minus 1 d n minus 1, okay, you can call it, it was what? Upper half, lower half. isn't it? So, that means this will be what? T n a lambda factor will come up, that lambda to the power half sorry u n minus 1 this is L. The last guy is d n. This will be the thing. From here, we will develop the adaptive algorithm in the next class. Okay, thank you very much. Please come prepared with this. I don't want to, time is running short. 1 or 2 lectures and course will be finished. Please come prepared on this.